So we have been discussing completeness, more on completeness. We will prove some theorems related to completeness in this class. Few more theorems. So I will try to prove 3 theorems in this class. Okay. No, you can finish it. You're saying something, so maybe you can finish it. Yeah. No problem. Okay. So this is the following purpose. This is to determine when it is complete for a norm linear space, a vector space with a norm. Okay. So V X or Vx norm the linear space. Okay. Then this is complete. X is complete. Of course, with respect to the norm. If and only if every absolutely summable series converges. What does it mean? That is, if you have a series, if summation norm xn, here we take the norm xn, which is a series of positive numbers. Okay, so if this is less than infinity, then converges. As see, this is a sequence in n. If you want to call, you can call this as yn. Okay, this yn as a sequence in the norm linear space converges. So this is a sequence in the norm linear space. Okay, let's take the sum. Up to this a finite sum, which of course makes sense, and this depends on this n. As a sequence, this is how we define a series converges in real n also. But here we have the sum, but the convergence happens in this vector space. This is about positive numbers, right? Norm xn is positive numbers. So if there is absolutely convergent, sequences are convergent sequences. Then it is complete. So you must be knowing that in real line, if we have a sequence which is, so if you have a series which is absolutely convergent, then it converges. But R is complete. That is why it is true. So here this is true for any vector space, any norm linear space. So that is it. So one way, this way, that is suppose V is complete, X is complete. So we assume every Cauchy sequence converges, every Cauchy sequence has a limit in X. Okay. And now, so we want to prove that, then we want to prove that every absolutely summable series converges. Okay. And for some series, norm xn, for some series, n equal to 1 to infinity is not that. Then we have to show that this series actually converges. What does it mean? You have to take this yn equal to summation k equal to 1 to n xk. Okay. Then we want to show that this is convergence. This is a convergent sequence. So we take this yn minus ym, this norm. That means k equal to 1 to n, k equal to 1 to m. So that will be n is less than m. Let's say n is less than m. And this is going to be k equal to n to m of yn minus yn. So this will be norm of x, x, k, sum will be inside. We are talking about the norm. So this is summation k equal to n to m x k, right? yn minus ym. Now this is just triangle inequality. This is less than or equal to k equal to n to m norm xk. Of course, this goes to 0 as m goes to 0. That's what it means by that this series is convergent, right? So this way is easy. This is what it means. The series converges if the tail sequences converges, right? The series converges means tail series converges to 0. Series, this is the series from k equal to 1 to n. This series converges as n goes to infinity. That means k equal to n to infinity. Suppose if we can calculate, that has to go to 0. That goes to 0. That's what it means, right? For this positive elements. Okay. So that means k equal to n to m, there should be a Cauchy sequence which should go to 0. Okay. So one way is clear. Now to prove this way, one way is very easy. You can't hear something, you tell me I have a serious problem. Today it has become very serious, my tongue problem. Some ulcer kind of. Okay, so to prove the other way, so suppose the second statement, suppose every absolutely summable sequence converges, then we want to prove it is complete. Okay, so we want to use the second statement to prove that it is complete. So suppose this is a Cauchy sequence. Okay. We want to prove it has a limit. That's what it means by it is being complete. Okay. So now if it is, so since it's a Cauchy sequence, there exists n1 something such that norm of so the distance between them xm minus xn1 is less than half for all m greater than or equal to n1. Okay. We can do for any m. So similarly, and there exists and choose n2 such that norm of x1 minus xn2 is less than 1 by 2 square or something for all m greater than n2. Like this, you go on and choose nk such that norm xm minus norm xnk is less than or equal to 1 by 2 power k. Okay. This is possible because it's a Cauchy sequence. Okay. So in particular, and also make sure that n1, also make sure nk increase, which is usually the case. But let me write it. Okay. Also, nk goes to infinity. Nk increases to infinity. Okay. Nk is increasing. It may happen for some other nk, but choose a bigger nk. Then, so in particular, x n k plus 1 minus x n k is less than 1 by 2 power k. That's right. So this implies summation k equal to 1 to infinity. Okay. So you call that as summation norm of x n k plus 1 minus x n k. Okay. This is less than or equal to summation k equal to 1 to infinity, which is 1 by 2 power k. These are all positive. So, but this is less than infinity. Right? So this implies the yk equal to xnk plus 1 minus xnk and summation. By the assumption is every absolutely summable sequences converges. Okay. So this just means yn equal to summation k equal to 1 to n. Okay. Yk plus yn, sorry, xnk plus 1 minus xnk. This converges as n goes to infinity. But this is this, what is called telescopic sum, right? So this is just x, maybe I should use n or something, k or n. K. K. So this is just x and k minus x1. So plus x1, right? X1 and then minus x1. Okay. xn1, right? Yeah, x1, the first term and then this. Okay, so this converges. So converges to some x in B, x. Okay. So in particular, x and k converges to xn1 is just a fixed element, okay, plus x. Okay. So we have a Cauchy sequence, Cauchy, and we have a subsequence, and there exists a subsequence x and k contained in subsequence of xn, which converges. By whatever we have seen, this implies xn is convergent, right? A Cauchy sequence, if it has a convergent subsequence, then it is convergent. So this implies xn is convergent. So we have proved the proposition. So this is a criterion, nice criterion. This can be generalized to metric space also. That doesn't look very beautiful. This is very nice. Every absolutely summable sequences converges, then it is complete. So this is sometimes it's very useful. So once you have finished, right? If you are writing, once you are finished, I'll start the next theorem. I proved 3 theorems related to completeness in this class. Okay. Maybe 4. Okay, fine. So this is something about completeness of a normal vector space. Next, we want to see what is called contraction mapping theorem. Next topic is contraction mapping. So I will define what a contraction is. X is a metric space. Okay. A T from X to X is a contraction. Contraction means it contracts, it reduces the distance. Okay. A contraction in a non-linear space, it reduces the norm of something when it is mapped. So it's something similar to that, but here it's slightly tricky. If there exists a C, which is strictly less than 1, strictly greater than 0, such that d of tx, t is this function, okay? T of tx, ty is less than or equal to c times d of xy. If it satisfies, c should be strictly less than 1. Okay? It shouldn't be the case that c equal to 1. You will see it is used. C is less than 1, then c power n will converge to 0. So we will use that, okay, because of that. Okay. So the theorem is the following. This is the contraction mapping theorem. Every contraction, this is a contraction. Every contraction has a fixed point. That's what it is. Okay. Provided this is complete. T is X is complete, then and T is a contraction. Then T has a fixed point. That is, there exists a X in X such that T of X equal to X. So, okay, so we want to produce a X such that which is a fixed point. So choose any x naught in x. And you will define a sequence. So we want to use completeness. We want to use the contraction property and we want to use the completeness. We want to get a fixed point. That's what we want to do. Okay. So we choose some x naught. Then we apply this t continuously. T x naught, t x naught, t of t x naught, so which is we call t square x naught, t power n x naught. So t power x naught, t power n x naught converges. That's what we want to do. Okay. So that's a limit, and that limit will satisfy the required property. So define, so let x1 equal to t of naught and x2 equal to t of x naught. So this is what we call xn equal to t power n. By t power n, we apply t n times of x naught. Okay. Then we consider this. We want to prove that this is a Cauchy sequence. Okay. D of xn, xm. This is equal to d of tn. Assume n is when m is greater than n. Okay. T power n x naught, t power m x naught is equal to. So each time we take the t out from both of them, we will get a c out, right? This is the inequality we want to use. Okay. So this is less than or equal to c of d of tn minus 1 x naught, tn minus 1 x naught. So we do it n times, we do it m minus n times. Okay. So c power n will come out because n is less than this. So here we will have x naught, and here we will have m minus n x. Sorry, we'll do n times. We'll do n times. We'll take n times because n is less than m. So it will come and it will become like this. Okay. Now what we do is the following. We use triangle inequality one by one. So c power n, I put it out. Then this is g of x naught x1 plus d of x1 x2. We go on like this, and t of d of x. I mean, this is xm minus 1, right? Xm minus 1. So xm minus n plus 1 xm minus n. Okay. So now this is equal to t power n. So here you have a t here. So you have it just like that. T x naught x1. Here you have a 1t, you have 2t, t square here. You can take 1t out. So which comes as a c. And then this is d of x naught x1, right? So you do like this, and you get c power m minus, so here it is 1 means m minus n plus 1, whatever, doesn't matter. But you get the one single number, one constant here. Okay. So this whole thing is, but this is all positive number. C is positive, everything is positive. So you can take it up to infinity, less than or equal to the whole thing by infinity. So this is less than or equal to, we have c power n here, and you have d of x naught x, and that is just the geometric series, right? Geometric series whose sum is 1 minus c, right? This is just a number. This is the number, right? D of x naught x1, fixed number. I mean, there is nothing depends on n or something. This is another number, so which is strictly, I mean, c is strictly less than 1. Okay, so this makes sense. So you have some number c power n, this goes to 0. I mean, m is bigger than n, so this goes to 0. So this is Cauchy. So this implies the sequence xn, it is nothing but t power n x naught is Cauchy. Since x is complete, tn x naught converges to some x or some x. Okay. Now you start this starts from x naught. You start from x1, tx naught doesn't matter. That will also converge to the same thing. Okay. So, but then t of, I mean, we want to show that t of x equal to t of, I forgot to say something. Every contraction is a continuous function. In fact, it's uniformly continuous. We have seen this inequality. This is less than this. It's uniformly continuous. So if you have an epsilon, then you take delta equal to epsilon by c. That will work. Okay, the continuity definition. So since T is continuous, T is uniformly continuous. In fact, I mean it's called Lipschitz continuous or something, but it also implies uniform continuity. T of limit xn, you can take it out, limit T xn. Okay. I mean, which is same as the sequence starting from, which is same as T power n plus 1 x naught, right? This also goes to x. Okay, so this implies T of x equal to x. Okay. There are some applications. Let's not look at it now. So this is an application of completeness. So if the space is complete, if it's a contraction, then we have this. And it doesn't work when C is not strictly less than 1. I don't have it now. I didn't look at it, but it's a standard counting number. I don't remember somewhere. I mean, I don't remember. Then C is equal to 1. This strictly, you use the factor C is strictly less than 1. If C equals 1, it will not work. Fixed point is also unique. That's clear, no? No. The fixed point itself, I think, will not work. Yeah, and it's also unique. That's clear, no? There exists a unique fixed value, right? Then there is unique fixed point. Uniqueness is clear, no? Exercise. You think of it. Yeah. X is R. Yeah. Correct. You are right. Yeah. That will preserve the distance. But that is an isometry. I mean, I'm saying even if you have less than or equal to, that will not work. You need a strict C. Yeah, that's an isometry. But you say it's an isometry. You are right. One such example. Huh? Isometry will not. He says isometry does not have a fixed point. You shift it. That does not have. More than that, I mean, even if you have less than or equal to, that will not work. Some function is there. I don't remember now. Okay. So this is our contraction mapping theorem. I will give something in assignment to do something more on this. Okay. I mean, I'll prove that. So this is not true if T of Tx Ty is less than T of xy. Okay. Then it need not be true that there is a fixed point for the general. But if it is compact, it will be there. So I will ask you to. So the assignment is to prove that when it is compact, prove that there is a fixed point. Compactness, you can do that. Okay. So I will post it. Okay. So next theorem we want to see is what is called Baer's category theorem. It's something about complete spaces. See, we say some set is some very small set. Small set means when there's something called see, rationals are infinite, irrationals are also infinite, but irrationals are much bigger set than rationals, right? They are uncountable, okay, something like that. So if you have, for example, if you have look at the continuous functions on some closed interval, okay, differentiable functions are there. They are dense. Okay, polynomials are dense. But then there are functions which are not differentiable anywhere. Not that. Okay. That is much more than this thing. What is called second category. First category, they are called second category. Okay. They are much richer. The point is, whenever you have some exotic object, I mean, irrational is an rational number is something, we call it rational. There's nothing about rationality about it. It is just that that number is which we can usually see. Irrationals, we don't, it's an, I mean, it expands. I mean, the decimal expansion is infinite. Okay? But then they are much more than rational numbers. Even though they are infinite, they are bigger in things. So like that, functions which are not differentiable everywhere, anywhere, not even a single point. So those functions are much bigger than, the other functions. A function is differentiable somewhere. Okay? So we will see that theorem. Okay? So to prove many of those theorems, this is one of the very important theorem which is used in many places. You can conclude many things from this. It's a very useful theorem, which is called Baer's category theorem. So before that, I want to make a definition. X is any metric space. Definition. Usually, a set A contained in X is said to be is nowhere dense. Usually, when we say dense, it is everywhere dense. Okay? Not dense somewhere. The closure is everything. So we say something is nowhere dense if a closure interior of a closure is empty. There is no open ball completely. If you take any element here, if you take the open ball, it will intersect with the complement. Yeah, that's what it means. So let us not take this definition because you have to take the closure. Let us assume A is closed also. Okay? I don't want to repeat each time when I say. When I say for us, nowhere dense means it's closed and it does not have any impedance. Okay? So, this is actual definition. But for us, this definition, we assume that it's also closed. Okay? So we have contained in X is nowhere dense. If F is closed, you don't consider other sets, okay? If you want to consider the closure, closed and interior of F is empty. Okay. So, see, the thing is, the countable union and all those things, that is also something like a rationality. It's like there is nothing exotic about it. It's like you can count one by one and then you can reach something. Even though it's infinite, it's something humanly possible, kind of. Okay? So if you take countable union of nowhere dense set, that's called a small set. That's also a meager set. Okay, so that is the definition. Definition 1. A set A contained in X is said to be first category or a meager small set. Meager if A is equal to union of countable union of. It's clear. If we have finitely many union of nowhere dense sets, it's again nowhere dense. But if it is a countable union of nowhere dense subsets, that is called nowhere dense Fn. If A can be written as countable union of nowhere dense subsets, then it is called meager. First category. Okay? So this is the definition. The theorem is any complete metric space is if it is not first category, we call it second category. Okay. So a set is second category. Set or X. We want to talk about X anyway. X is second category. This is just names. Okay. What it means is clear. What it means is you cannot write it as countable union of meager subset. Second category, if it's not first category. First category, okay? Yeah, it's complement. What do you say? Yeah. It will be open also. It will be open yes. Yeah, that's why I use the closeness, included closeness method. It is open and dense. Okay? So good point. So note, if F is nowhere dense, so NWD, nowhere dense, I write it NWD, then F complement is open and dense. It is very important, open and dense. Yeah, one more question. That's all. Okay. So the complement of the statement is yeah, open dense subset is I mean, it's not empty, it's not the following. It's not it's also not first category. That's what I want to say. It is dense. What is the right statement? No, intersection of open dense subset is not just it's not empty. This says that first category it's not empty. I mean, it's more it is dense. That's the statement I want to make. Okay, that's the theorem. X is complete. Okay. We'll come to the corollary later. This yeah, one will follow the other, but I want to say I want to try to make the equivalent statement. Maybe my definition of first category is not the, maybe I can make it better. I mean, is it like, okay, let me make the statement. X is complete, and suppose UN is a sequence of open dense subsets. Okay, open and dense subsets. Okay. Then the statement we need is intersection is non-empty, but that intersection UN is also dense. Because it need not be open, it is also dense in X. So if it is open and dense, then I mean F is nowhere dense, if and only if. This is the mistake. And the complement is so if you take UN complement, they are nowhere dense subset. And UN complement is not just, I mean, UN complement is still meager. I mean, union of UN complement is again nowhere dense because its complement is dense. To prove. Let's prove this and come to the corollary. Okay. Meager means it's a union of nowhere dense subset, countable union of nowhere dense subset. First category. And X is complete, it's not first category. We say something more, but in particular, it's not first category. Okay. So it is just some tricky way of, so we claim the following. Assume X is complete, of course, X is complete. We assume X is, no. So completeness, we have proved counter intersection theorem. We will use completeness for that. Okay. Now we don't need completeness. This statement, whatever the right thing we make, I think it's true for general claim. This is the claim. I prove the claim, then it follows by counter intersection theorem immediately. The claim is the following. Given we are forced to take closed ball because counter intersection theorem is for closed set. Okay? So given a closed ball means it has an interior, okay? And it's also closed. I mean, that's the point we need. That's the fact we need. We are going to use. So given a closed ball B and an open dense subset, dense some U contained in X. So given these two things, there exists so closed ball of in counter intersection theorem involves the diameter. Okay, the last class we proved, some of you are not there, some of you are there. So the closed ball with the diameter, something about the diameter. Diameter of B, some less than some R, okay, and the open lens U containing X. There exists another closed ball. There exists a closed ball, which we call B prime, which is contained in both B intersection, both B and U, okay, such that the diameter will decrease, such that the diameter of B prime, I mean, this is just, we can take the diameters smaller and smaller so that we will be using a sequence of systems. We will be using, you use this argument again inductively. Diameter of B prime is less than R by 2. Okay? Maybe equal to R by 2. If you choose something, then you can choose something smaller also. So proof of the claim, it is trivial. I mean, it is clear, no? Should I even write it? You have a closed ball B. That means it has the open ball inside that. I mean, it's just the open, it need not be the closure of the open ball, but the open ball is inside that. Okay. Now you have an open ball which intersects with another open set. Because this is dense, okay, U intersection, the interior of B is non-empty. Okay, both are open. So you have an open ball, this is open. Since U is dense. Since U is dense. Okay, and both are open. So there is a open ball contained in this. Okay, that will have open ball is contained in that will have the radius less than this R. Now you take closed ball of R by 2, which is contained in both of them. Open ball of R contains a closed ball with the radius R by 2. Okay, so there exists a, it's clear. So there exists a B naught, B prime with R by 2 radius. I mean, I said diameter, that doesn't matter. I mean, I said diameter, diameter also you can make it half, radius also you can make it, okay, with the diameter of, it's clear, okay, B prime contained in B intersection. It's clear. I have just repeated the statement. Okay, it's clear, no? Okay. Now we want to use this inductively. Okay. Now suppose claim is proved. Now suppose UN, a sequence, open dense. Okay. So you choose some ball, some closed ball. Okay. Choose some P naught contained in it. Okay. Some closed ball. Okay. So this U1 is open and dense. Okay. So there exists a B1, so closed ball with diameter R. Okay. So there exists a B1, which is contained in B naught intersection U1 with diameter of B1 less than R by 2. Continue this. Now choose B2. These are all closed ball. Okay, closed ball. Closed ball or closed set, you can say whatever. B2 contained in B1 intersection U2. Okay, with diameter B2 less than R by 2 square. Okay, cool. So continue this. So there exists Bn contained in Bn minus 1 intersection Un with diameter of Bn less than or equal to 1 by 2 power n. Diameter goes to 0. Okay. So now the Cantor intersection theorem, which we approved in the last class. So now theorem implies intersection of all those Bn singleton. Now this x is in all those Un, right? Intersection of Un. Okay. What we approved, we started with some closed ball B. Okay. This implies interior of B intersection of Un and it could contain is non-empty. That's what you approve. Started with the ball, open ball, which is say which is a open ball of that, or the open B, whatever you take. What does it mean by something is dense? You take any open ball, it should intersect with that. So you take an open ball, I mean, or the closed ball, doesn't matter. Okay, you can take the closed ball itself. Okay. Is it clear? So that will contain that. That's all. So we have proved it is dense. Okay. So what does this say? Corollary. X is complete implies its second category. That's enough for us. Okay. Complete implies X is second category. It cannot be written as countable union of nowhere dense subset. You take the complement, that will be open and dense. The intersection of that will be empty, which is not possible. So there are many consequences to this bare category theorem. It's heavily used everywhere in functional analysis. There are many theorems. And there is something called, which is not the theorem I am going to prove. I'm calling something as uniform boundedness principle. In functional analysis, it's slightly different, something else. It's for linear maps. Linear maps are not bounded, right? Linear maps, if you multiply by alpha, it will value also. Linear maps are something which satisfies this. Linear map in a vector space. Linear map alpha x equal to alpha times Tx. Okay, this is one of the property. I mean, it's also respects the addition. Because this is a linear map. So once you have, so this means that if Tx is there, then alpha times Tx is also, you can take alpha to be very big, some positive number. So linear maps will be unbounded. But there is a boundedness definition for a linear map, which is different. So, and the theorem is about that. But we will make a different definition, different, huh? Bounded in the linear map, correct. So that's right. Okay. So you have looked at those things. Okay. So, yeah? No, you have looked at those things, I said. Yeah. So that's the definition. Yeah. So you can, so that is the boundedness. So the statement is about that, but if we make a different statement, you can take the bounded, any bounded bar and then use this statement also, which will be true. But then linear map has some properties. You can, any unit ball somewhere can be just by shifting, translating, you get another unit ball, or you can enlarge it, and those properties are there, which will be used. So here it's a different theorem. It also we can call it as uniform bounded. See, if you have a function which is pointwise bounded, I mean, no, if you have a collection of functions, each function is bounded, then the whole, okay, what is the one? Pointwise bounded, right? We let so XDM complete matrix, please. Actually, you don't need completeness for this. You can work with the completion if it is a nice function, nice uniform. Linear maps are uniform continuous function. So you can actually extend to the completion. So whenever you can do that, some uniformly continuous function, then you don't need it to be complete. You can extend to the uniform, you can extend to the completion, and then get the same statement. Okay? But anyway, let us assume complete metric space. So this is a collection of all those functions from collection of functions. This is a this, and then get some functions from R or C. Okay. C or R, doesn't matter. Continuous. I'm just wondering where the continuity is used in the proof. Let's see. Okay. Such that for each x in x, there exists a mx something greater than 0, some number, such that f of x, you fix the x and f is in this collection. Okay. This is all, I mean, this supremum is finite, so this is less than mx. Okay. Is bounded for each x. This collection is bounded. Okay. Then it is uniformly bounded. That's what it is. Then, I mean, uniformly bounded on an open set, which is a strong statement. If for each x something happens, then you have a collection which is an infinite collection. Open set will be some infinite collection, right? So then there exists a open, which is a very strong statement, or the open ball where this happens. U contained in x, such that f of x, f in this f, where x is open, and m greater than 0, single m greater than 0, f and x in u. Okay. This supremum is finite, or this is all less than m. Or the infinity norm in this u is less than that. That is the uniform bounded, right? Infinity norm, this says that if it is pointwise bounded, you fix a x and take this f. Pointwise, this is bounded, f of x, this is bounded. So the whole f of, all f of x is less than mx. Then you consider the infinity norm on this u, restricted to this u, which is the supremum for this. Okay? Or something supremum of x in u. Okay? F of x, mod f of x. I have to put mod, sorry, because I'm using complex number. I have to use mod, sorry. Everywhere. Mod f of x, supremum f in this direction, is less than infinity. Sorry, there is a m such that it is less than. Okay? This is the state. So the proof follows from Barre's theorem more or less immediately. As I said, you can use any, x need not be complete. You can use some uniformly, if you use uniformly continuous function, then you can extend to the completion and prove there, and then you get this statement. Let an equal to all those x in x and such that f of x, mod f of x is less than n, less than or equal to n. Is a for all f. Then given any x, you will find, given any x, you will find a n such that this happens, right? Since by definition, so x is equal to union of a. Where the continuity is, this is a closed set. That is where the continuity is used. A is closed. Since F is continuous. All this, I mean, why is it? Because it's a intersection of closed set is closed set. Okay. AN is equal to this, right? AN is equal to F inverse of mod F inverse. Mod F is also continuous. Mod F inverse of this 0 again. Okay. That's why I put it's better to put less than or equal to 0 n, and then intersection over all F. This is a closed set. Inverse image of continuous closed set is closed set. When you are taking intersection, arbitrary intersection, doesn't matter. So it's all closed set. Okay, so use closed. This is where we need continuity. Okay? Is closed. Yes. Okay. Since F is continuous. Okay. Okay. So now we have X is equal to union of AN. Because given any, given any X, you have to prove it. This is, of course, everything is in AN. You don't have to worry. So given any X, it has to be in one of those AN. That's what you want to say. Given any X, that says that there exists a single M where everything is less than that. So you can take a bigger M and that will be inside. Okay? So it's clear, no? Given any X, X is in AN. That's what you want to prove. By definition, that there will exist a M. That's what the condition says. Okay? So this is true. Okay. Now, since X is complete, all these AN cannot have interior empty. ANs are closed. Okay. Now, since X is complete, okay, it's second category. That's theorem. Implies there exists a AN naught such that interior of AN naught is not equal to empty. So what does it say? So there exists a open, let's say open set, okay, contained in AN naught. Open ball is contained, so let's call that open set. Okay? Open set is contained in AN naught. Okay? So it is in AN naught means what? For all X in U, F in F, F of X, mod F of X, less than M naught. That's what we want to prove. And the whole open set, this is. So this is uniform boundedness. I'll stop here today. Any questions? No questions? Yeah, tell me, huh? Which formulation? Yeah.
Should be considered AN, BN to be F mod inverse of N to infinity. That should give us the proof with that. I want to use.
Oh, you want to use the other way? Right. Yeah. But that is slightly more general. You don't need it, no?
No, this is the same.
Same thing, of course. You have to take the complement. That's right. Yeah. But this is the more direct thing. Yeah. You have to take the complement, you have to come back. No, you don't do that. And actually, in the assignment, there is the guy who came and he pointed out one of the statement where the uniform continuity has to be extended to the dense to closure. No, you need the range to be complete, because you will take sequence and you will use the Cauchy sequence and other things. So range should be complete. I forgot to mention. So please use that.